Okay, this is the last video for day 2 types, where I want to talk a bit about higher order functions. We've actually already seen one or two in argmin and argmin3, so I want to talk about it in detail. Coq, like other functional programming languages, or Galena I should really say, uh, is a functional programming language, which in part means that functions are first class. You can define them on the fly, you can pass them around as arguments to other functions, you can have functions create them. Functions are very much a thing that our programs are going to be about, and that is a real beautiful flexibility that it gives us. This is a style of programming that I really enjoy and is very expressive and powerful. So as a first example, I want us to look at this function, do it 3 times. This is a function, right? It takes an argument f of type nat arrow nat, an argument n of type nat, and it's going to return a nat. And what does it do? It applies f to n 3 times. Now what's interesting about this is we don't know what f is, just in the same way we don't know what n is, but we've been able to write the skeleton of our computation in some sense, saying like, oh, this is what we'd like it to do. This notation is our way of saying, hey, tell me the type, and then also I'd really like to know that this is the type of it, right? So do it 3 times is type nat arrow nat, arrow nat, arrow nat is how I would pronounce it. You have to make sure you get the dance just right. Which is saying, you give me a function from nats to nats, you give me a nat, I'll give you a nat back. So let's look at some examples. It's really key. So we've given you the answer, but it's really key to think through why does it do that for you to really understand what's happening. So do it 3 times, -2, 9. What's this going to do? Here's the function f, here's the number n. Right, so this should really be, before we get Coq to confirm that it really will be 3, what's this going to be? It's going to be -2, -2, ooh, how do you spell? 9. Right, and if we sort of put on our let me evaluate hat, right, that's going to be 7. That's going to be 5. That's going to be 3. Okay, hopefully makes sense enough. Coq agrees. Now we can also say do it 3 times fun n s of n. So here we're defining a function. We'll see the full detail on this in a second. And this says, oh, take s of n 3 times. You know, that's just the same as saying do it 3 times s. What's happening here? Well, fun is defining a function live, right? This is saying let f equal, or f of n equal s of n in f of f of f of 2. That's morally what's happening here. So that's really the same as, let's do it this way. Okay, so what's going on here? Let's reduce it outside in like we just saw before. Okay. So this is a little function right here. This 2, well, that's the argument to this little function right here. This is an anonymous function right here where we'll pass in 2. So that's going to be s of 2, which let's just go ahead and change that to 3. Okay, that's going to pass in here. So that this 3 will pass in for the n. It'll be s of 3, which is also known as 4. And then this will be, the 4 will be n, so we'll get 5 out. Now, this fun n s of n, we could have just written s. S is a constructor, but if you look at its type, s is a function, right? It takes a nat to a nat. The successor operation is a function. So we can treat it, this is one of the ways in which functions are first class, we can treat it just like a function and pass it in and say, okay, do it 3 times s, and it'll give us the same answer. Right, so we can in general, like we just saw above, construct a function on the fly without giving it a name. So here, fun n times n, this is the square function. Check fun n times, this says, tell me what type this is, it'll tell us it's a nat or a nat. And then fun n times n is the function that when you give it n, returns n times n. Let's do a quick compute with it. There's our function. Let's compute the square of 5. Should be 25, huh? Brilliant. Right, so I could have said definition square n is a nat, or nat, n times n. Right, that's fine. I could have also said something like this. Square prime is a function. What is it? It's this function. Here I've given the whole type of square prime, no arguments, but then I wrote a fun. In fact, the way Cox sees thing, this definition is exactly the same as that definition. We'll see a little bit more about this in the coming days. There's a command print that will show it to you. So print square, it says, oh, square is that. But look, we defined square using this notation, but is printing it back out to us using this fun notation. Fun is the truth. Right? Cox sees these as identical. So these higher order functions are a super useful way of sort of in a one-off way saying, hey, this is the function that I wanted for working with some other higher order function that you wanted to. Where, to be clear, do it 3 times is a so-called higher order function because it takes a function as input. Okay. So let's play with that. Let's look at that with do it 3 times. Here's do it 3 times, fun. Here's the function that adds 2 numbers, right? Okay, why? Well, we started the derivation for you here. I want you to do it on your own. It's not for homework. I just want you to figure it out. Right? I think doing this on your own will be really informative in that same style of the substitution semantics we talked about. Okay. Last thing, last super new thing, is that if you want to define a recursive function on the fly, you can do it using fix. So here, for example, we on the fly define a function I'll call even b prime that does the same thing as even b. Right, so this is saying fix is just like fun, except for you then give the name of the function you want to define recursively, and then you can make recursive calls. All the usual constraints apply. It has to be well typed. There has to be some decreasing argument. All of that is pretty standard for Coq, but this is just another affordance that you have. Okay. All of this, not of huge import yet, but we're going to see these things more as we program a little bit. Okay. Well and truly the last thing, functions that construct functions. So far we've had higher order functions that take functions as input. Here's something that treats a function as output. So this is something called constFun. It again has this type parameter that we're not going to talk about in great detail, but it means that we can use it with any type if we want to. And it says, you give me something of whatever type, and then I'll give you back a function that takes a nat and gives you that thing back. Okay, what's the function that we give back? Well, it takes the nat k and ignores it, and it gives back the thing it got in the first place. So this is called the constant function because whatever your input, it's the thing that you set up earlier. So f true, this is the constant function true. Right? If you run f true of 0, you'll get true. If you run f true of 23, you'll get true. Whatever you run it on, you'll get true because it always returns that. constFun 5, here now using a different type for x, you'll get 5 every time, doesn't matter what you apply it to. All right, now we've already seen some of these details, but it's worth reiterating now that we've seen a little bit more. A 2-argument function in Coq is actually a function that returns a function. So you might think this constFun is weird and exotic, not least because of the curly braces, but like, okay, well, this fun keyword shows up, but you've already written functions that return functions. Plus is a function that returns a function. Look, here's the +3 function. +3. Huh. Interesting. +3 is the function that adds 3 to some number it's waiting for. We can use print, if we can type, to see that like, oh, it's just plus applied to 3. Here, nat.add, it's catching the standard library, which is the one we'll be. We can run it. +3, 4 gives you 7, like you might expect. +3, 0 gives you 9, like you might expect. And then, in fact, you don't need to do a definition. You can do this partial application right here. Okay, the final exercise in the homework. We've given you a program here. You can run it and you'll see the answer. And it might just not be what you think. Right? Looking at the code here, you might think you're going to get one answer and then be surprised to find that you get a different. And I'd like you just to explain what it is. Just a few sentences. It's not a big deal. You don't even have to show a derivation with those equalities, though that's fine to do. It's just what's going on. right? There's something subtle happening here with partial application. What this is, where we've applied only some of the function's arguments. There's something special happening here, and I want to make sure that you understand what it is. Okay, that's it. These are all the terms we need. Next week, we'll start to write more interesting programs. So you might feel a little bored. You might feel a little confused. You might feel like it's easy or that it's inscrutable. All those are great feelings to have. I think things will really start to click in a little more next week as we start to do a little bit more programming. Okay. It's Sunday right now when I'm recording this, so I'll see you on Monday. When you're watching this, maybe I'll have already seen you on Monday. So think about that. All right. Talk to you soon.